we've seen how we can use constant functions to approximate a function to approximate an integral, and that was the right hand, left hand, and midpoint rule for approximating integrals. And we also saw how we can approximate a function with straight lines on each subinterval, and that gives us the trapezoid rule. But if using lines is better, since trapezoids are better than left or right endpoints, then surely parabolas would be better than even lines. So the idea is on a subinterval, so let's break, so on this integral that we were approximating from 0 to 2 sine x squared, if we break this interval into 4 pieces again, maybe on each interval we can approximate the function with a parabola rather than with a straight line. So the data points that we have, right, typically in applications, you don't get to choose where your data points are located. You sort of are handed a set of data that someone went out and collected. So let's say that these are our data points. And we want to fit parabolas to approximate this function. Well, suppose we tried to have a parabola for every subinterval. On this first subinterval, we only have 2 points, one at each end of the interval. And if you only have 2 points, that's not enough information to fix a single parabola. There are lots of parabolas that go through 2 points. This is very different than lines, right? Lines, 2 points gives you 1 line, but 2 points doesn't give you 1 parabola. It gives you lots of different parabolas. It turns out to fix a single parabola, you need 3 data points. So what we're going to have to do is take these subintervals in pairs. So rather than having a parabola for every subinterval, we'll have a parabola for every pair of subintervals. So on this first pair of subintervals, there's a unique parabola that goes through these 3 points. And, maybe it looks something like this, right? So on the interval from 0 to 1, we're going to use just this parabola. And on the interval from 0 to 1, the area under the parabola is almost the same as the area under the graph of the function. On the second pair of subintervals, so from 1 to 1.5 and 1.5 to 2, again we have 3 data points. So again we can find a unique parabola that goes through these data points. And maybe it looks like this. Okay, you can see if you go outside of the pair of intervals, the parabola stops following the function, but as long as your intervals aren't too big, the parabola should follow the function pretty closely on this pair of intervals. And then the area under the parabola on these 2 intervals is very close to the area under the graph of the original function. So what we need to do to use this idea is come up with some way, some formula for finding the correct parabola and then finding the area under that parabola. So what we need is, if we have 3 data points, say x sub I minus 1 and then f of x sub I minus 1, so that's 1 data point. The next data point along is x sub I comma f of x sub I. And then the data point after that is x sub I plus 1 comma f of x sub I plus 1. So if we have these 3 data points, what we need is some way of finding the parabola that goes through them. And once we have that parabola, we need to find the area under the parabola from x sub I minus 1 to x sub I plus 1, right? Because once we have one of these parabolas, we only care about the area under it on the interval that we used to find that parabola. So this is actually a lot of algebra to go through. So I'm going to just jump to the final result and put the messy calculation in a different video. But here's what you get. So here I've written the data points using k's instead of i's. So if we have these 3 data points, and these are 3 data points that are adjacent in our data set, and they have to be evenly spaced. So the spacing between these data points is delta x. So if we take these 3 data points, this one, x sub k minus 1, and f of x sub k minus 1, x sub k and f of x sub k, and then f of f sub k plus 1 and f of x sub k plus 1. Then if you find the parabola that goes through the 3 points and then find the area under that parabola, here's what you get. Turns out that it's actually pretty nice. It's just delta x over 3 times the first function value, 4 times the second function value, and the last function value, all added together. So this is a surprisingly nice formula, I think. So this is just for a single pair, for 3 data points, which remember is a single pair of subintervals. When we break our subintervals into pieces, each pair of subintervals gives us one of these parabolas. These data points are the 2 data points on either end of the subinterval, here and here. And then there's the data point that's in the middle of the pair, which is there. Okay, so this is for a single pair of intervals, but what happens if we have even more data points? So more subintervals, right? More pairs like this. So for this to work, we need an even number of subintervals so that they break up into pairs. So an even number of intervals means we're going to have an odd number of data points. Right, so since we number our points from 0 to n has to be even for this all to work out. Okay, so let's write down, what we're going to do is write down what this formula gives us for when we have many pairs of intervals. So for the first pair of intervals, that's going to, we get delta x over 3, and then, right, the first one is multiplied by 1, so f of, the first pair is going to start at x sub 0, and then the middle one gets a 4, so 4 times f of x sub 1, and then the right-hand point gets a 1, so 1 times f of x sub 2. So that's for the first pair of subintervals. Now we can add to that the second pair of subintervals. So again, that's delta x over 3 times. So the second pair of subintervals, if you look at our diagram here, the second pair of subintervals starts where the previous pair ended. So that means our first term here is 1 times f of x sub 2. And then the middle one gets a 4, so 4 times f of x sub 3. And then the end point gets a 1, so f of x sub 4. Okay, that's the second pair of subintervals. Plus, now let's write the third pair. The third pair of subintervals. So again, it's delta x over 3 times. Now the third pair starts where the second pair ended, so that's f of x sub 4. And then the midpoint gets a times 4, so 4 times f of x sub 5 plus f of x sub 6. Okay, and so on. The last pair is going to be delta x over 3, and then f of x sub, well, the very last one is n, but we're 2 before that, so n minus 2, plus, and then the next one is a middle point, so that gets a 4. 4 times f of x sub, we're 1 before the last one, so n minus 1. And then the very last one gets a 1 because it's an end point, so f of x sub n. Like that. Now let's look at all of these pairs that we wrote down, or the area for all of these pairs that we wrote down. All of them have a delta x over 3. So for our total, let's factor out that delta x over 3. Okay, so our very first one, that's just f of x sub 0. And then the next one is 4 times f of x sub 1. The next one is f of x sub 2, but it shows up twice, here once and here once. So there's 2 copies of it. So plus 2 times f of x sub 2. The next one is x sub 3, and that's a middle point, so it gets a 4. 4 times f of x sub 3 plus. The next one is x sub 4, but again, it shows up twice. So 2 times f of x sub 4. This is getting a little tedious. I hope you get the idea. Next one is a midpoint, so it gets plus 4 times f of x sub 5 plus. Now x sub 6 shows up once here, but remember there are a bunch of other pairs in the middle here, and x sub 6 shows up once here, but it also shows up at the beginning of the next line. So there's a 2 f of x sub 6, and so on. You see there's this pattern where the middle points get a 4, and the end points get a 2 because they show up once on the right-hand end and once on the left-hand end. So it keeps alternating, 4, 2, 4, 2, 4, 2. So dot, dot, dot. So for these last few, right, there's this f of x sub n minus 2, but remember n minus 2 also shows up on the line before as a right-hand endpoint. So there's 2 times f of x sub n minus 2. We're almost done. Now there's a middle point, so that gets a 4. So 4 times f of x sub n minus 1 plus, and then for the very end point, the far right-hand end at x sub n, that only shows up once. There is no next line for x sub n to show up as a left-hand endpoint. So x sub n really only shows up once. So 1 times f of x sub n. So we get this pattern, right? We get this pattern, which is called Simpsons Rule. When you have an even number of intervals, so n is even, and so you have an odd number of data points, and all of your data points are separated by delta x, then you can approximate the integral by delta x over 3, and then it's all of your data values, but the pattern for the coefficients is 1, and then 4, 2, 4, 2, 4, 2, 4, 2, 4, and then the very last one is 1 again. So again, the pattern is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. All right, so with that in mind, let's actually try this. Let's try Simpsons Rule. And we're going to calculate the integral from 0 to pi of sine of x dx using 4 subintervals. And we could calculate this integral exactly, but the reason I want to approximate it is so that we can compare the approximation to the exact value and see how good the approximation actually is. Keep in mind that we're only using 4 subintervals, and using just 4 subintervals usually doesn't do a great job. If we use just 4 subintervals for right-hand endpoints or left-hand endpoints, it would not do a very good job. And if we used 4 subintervals for trapezoids, it would do a better job, but still not great. So let's see how Simpsons Rule does. So our function for this situation is sine of x. So for Simpsons Rule, usually use s, so s sub 4. I guess we need to know delta x first. So delta x is pi minus 0 over the number of intervals, which is 4, so pi over 4. So pi over 4, that's delta x, over 3. And now we do the pattern of coefficients. So first we need f of x sub 0. So this is sine of, I guess let's draw our interval. If we're going from 0 to pi, we're breaking this up into 4 pieces. So these are going to be our x values, right? Pi over 0, pi over 4, pi over 2, 3 pi over 4, and pi. Okay, so sine of 0. The next one is 4 times f of x sub 1. So 4 times sine of pi over 4. The next one is a sort of overlapping endpoint, right? So that gets a 2. So 2 times f of x sub 2. 2 times sine of pi over 2. Plus, now the next one gets a 4. 4 times f of x sub 3. So 4 times sine of 3 pi over 4. Plus, and then the last one is just f of x sub 4. So that's sine of pi. All right. So this is pi over 12 times sine of 0 is 0, plus 4 times sine of pi over 4 is root 2 over 2, plus 2 times sine of pi over 2 is 1, plus 4 times root 2 over 2, plus sine of pi is 0. Okay, so pi over 12 times, looks like we get, right here's 2 root 2, here's another 2 root 2, so 4 root 2 plus 2. So what does this all come out to be? Let's dump it into a calculator. 4 times square root of 2 plus 2. So all of that times pi divided by 12. So I get 2.004559 8, I guess. Okay, now let's find the exact value, right? It's impossible to know how good this is if we don't know an exact value. So just to compare, let's integrate from 0 to pi sine of x dx. So this is minus cosine x from 0 to pi. So minus cosine of pi is minus 1. Cosine of 0 is plus 1. And so this whole thing comes out to exactly 2. So the exact value is 2, and the approximate value is, well, look, it's good out to the hundredths place. We're only off by 4 or 5 thousandths. And remember, we just used 4 subintervals. So for using so few subintervals, this is a really good result. You can see if we programmed this pattern of coefficients into a calculator, or into a computer, and used 100 subintervals, the approximate integral would be very, very close to the exact value.